Hello students, today we will discuss another analytical technique known as voltammetry. The lecture plan includes the details of voltammetry, linear, sweep and cyclic sweep voltammetry. Then we will compare polarography versus voltammetry, the Randall-Sevcik equation, pulse techniques and stripping techniques, and then the applications. The first question comes to the mind is, what is voltammetry? Voltammetry is the general name given to a group of electroanalytical methods in which the current is measured as a function of applied potential at solid electrodes. A plot of current as a function of applied potential is called a voltammogram and is the electrochemical equivalent of a spectrum in spectroscopy, providing quantitative and qualitative information about the species involved in the oxidation or reduction reaction. This is a general look of a typical linear sweep voltammogram. Here you can see we have potential on x axis, current on y axis, and if we begin oxidation, the current starts from 0, reaches to a maximum value and then starts decreasing. And therefore, in voltammetry we get a peak rather than S-shape curve. Little later we will discuss as to why we get peak in voltammetry in contrast to S-shape curve in polarography. The setup of voltammetry is little bit similar to polarography, and here a 3 electrode cell setup is used for measurements. The working electrode is a solid electrode which may be platinum, gold, silver, copper, carbon surfaces, etc. The reference electrode normally used is SCE or silver chloride electrode. Auxiliary electrode is platinum wire, and that is why we use 3 electrode system here. This is a common cell which is used for electrolysis. Here you can see we have a counter electrode which is platinum electrode, we have a reference electrode which may be saturated calomel electrode or silver chloride electrode, and this is working electrode. This is a Teflon cover which is provided on the vessel so that oxygen does not interfere, and this is a purge tube through which we bubble nitrogen or any other inert gas through the solution. Now the question comes, why we use 3 electrode system and not 2 electrode system, which is very common in polarography. 3 electrode system is preferred over 2 electrode system because with 2 electrode system potential drop becomes significant in non-aqueous solutions which offer resistance to the free migration of ions, and thus erroneous results are obtained. However, in 3 electrode system the potential changes of the working electrode are measured independent of changes that may occur at the counter electrode, and in such system 99% current flows between working and auxiliary electrode, and therefore better potential control is achieved using 3 electrode system. This is a general diagram of 2 electrode system and 3 electrode system. In the 2 electrode system, we have a working electrode, we have a counter electrode or reference electrode, and the power supply provides the input. We measure here current and we measure voltage here, whereas in 3 electrode system, we have a reference electrode, we have a working electrode, and then we have a auxiliary electrode. Here 99% current flows between working and auxiliary electrode, and reference electrode is used only for measuring potential, and therefore, less than 1% current flows between working and reference electrode, and therefore, the potential of the working electrode remains constant. Now, first comes reference electrodes. A reference electrode is an electrode which has a stable and well known electrode potential. The high stability of the electrode potential is usually reached by employing a redox system with constant, that is buffered or saturated concentrations of each participants of the redox reaction. Commonly employed reference electrodes are shown below. One of them is silver chloride reference electrode. We have discussed this in potentiometric titrations, but I am just explaining it once again. Here we have a porous plug at the bottom of the tube, and which is just above the plug we have solid KCl plus some AgCl, and we have a platinum wire coated with silver chloride, and here we have a solution which is saturated with KCl and AgCl. Now, this electrode is very similar to the calomel electrode, where we have a porous plug again here. We have here, this is a glass wall, solid KCl, and here we have mercurous chloride filled with Hg, that is mercury, in the inner tube, and we have a glass wool opening at the bottom of this tube. Then we provide a wire for connection, and this is known as calomel electrode. So, both the electrodes are somewhat similar and they are widely used as reference electrodes. Now, let us discuss in a little bit more detail the silver chloride electrode. The electrode functions as a redox electrode, and the reaction is between the silver metal and its salt silver chloride. Wire is immersed in a solution containing chloride ion, which may be 3 molar NaCl, 3 molar KCl, may be saturated NaCl or saturated KCl. A porous frit, as I have shown you, is used at the junction between the reference electrode solution and sample solution. The corresponding equations can be presented as silver chloride solid takes an electron to give silver solid plus chloride ion. The standard electrode potential for this reaction is 0.210 volt in 3 molar KCl and 0.197 volt in saturated KCl. Nernst equation for this electrode can be written as E is equal to E naught minus RT over NF ln A, that is activity of chloride ion. The potential is, however, very sensitive to the traces of bromide ions, which make it more negative. Then the calomel electrode. Here the saturated calomel electrode, normally represented as SCE, is a reference electrode based on the reaction between elemental mercury and mercury chloride. The aqueous phase in contact with the mercury and the mercury chloride Hg2Cl2, known as calomel, is a saturated solution of potassium chloride in water. The electrode is normally linked via a porous frit to the solution in which the other electrode is immersed. In cell notation, the electrode is written as chloride aqueous separated by Hg2Cl2 solid separated by Hg liquid with standard electrode potential as 0.210 volt in saturated KCl. The calomel electrode contains mercury, which poses much greater health hazards than the silver metal used in the silver chloride electrode. Now, the question comes how this current in voltammetry varies. When the applied potential to the working electrode exceeds the reduction potential of the electroactive species, a reduction will take place at the surface of electrode. Thus, electroactive species diffuses from the bulk solution to the electrode surface and the reduction products diffuse from the electrode surface towards the bulk solution. This creates what is called as Faradaic current. The magnitude of the Faradaic current is determined by the rate of the resulting oxidation or reduction reaction at the electrode surface. Two factors contribute to the rate of the electrochemical reaction. The first one, the rate at which the reactants and products are transported to and from the surface of the electrode, which is known as mass transport. Second, the rate at which electrons pass between the electrode and the reactants and products in solution, which is known as kinetics of electron transfer at the electrode surface. This is an example. Here you can see ferrocyanide, when reaches to the electrode, it gives an electron and becomes FeCN6 4 minus. That is, here ferrocyanide is moving towards electrode, and when it gives an electron, it moves away from the electrode. Then comes sweep technique. We have linear sweep and cyclic sweep voltammetry. The first one is linear sweep voltammetry, which is a general term applied to any voltammetric method in which the potential applied to the working electrode is varied linearly in time. The slope of this ramp has units of volts per unit and is generally called the scan rate of the experiment. This is a graph showing the change in potential with time. You can see here the potential is changing linearly with time, and the slope is delta E divided by delta time, and this ramp can increase anywhere from few millivolts to several volts per second. And here we are getting corresponding change in current with applied potential. You can see here at 0 potential the current is practically 0, and here it goes on increasing, reaches to a maximum and then decreases. This curve has two important parameters. The maximum of the current is called as EP, that is the peak potential, which means that the potential corresponding to the maximum current is known as EP, whereas the difference of current from maximum to the minimum current at the starting potential is known as IP, which is peak current. Now, let us see how voltammetry differs from polarography. In voltammetry, as I have told you, the working electrode is always a solid electrode like copper, lead, zinc, carbon surfaces and so on. Whereas in polarography, it is always dropping mercury electrode represented as DME. Result is shape in current versus potential curve. You can see here in polarography we get S shape curve. The curve begins with minimum current, reaches to a maximum current and becomes constant. Whereas in voltammetry we begin with less current reaches to a maximum and then the current starts decreasing. So, in polarography we have a S-shaped curve, whereas in voltammetry we have a peak in place of sigmoid S-shaped curve. The question is why there is difference in behavior. The reason is in polarography initial conditions are generated due to the growth and fall of drop, which means concentration gradient is established afresh at each drop. Whereas in voltammetry, as the duration of electrolysis increases, depletion of electroactive species from the electrode surface occurs, due to which concentration gradient decreases. There are many types of voltammetric techniques such as linear sweep, which we have already discussed, cyclic voltammetry, pulse voltammetry, differential pulse voltammetry, stripping techniques. Let us now come to linear sweep voltammetry. In this case, the peak current is given by the Randall-Sevcik equation, which is I p, that is peak current, is equal to 2.69 into 10 raised to the power 5 n raised to the power 3 by 2 a c d half and v half. Here we must remember this small v is different than capital V, which we use for volts. Small v in voltammetry we use only for sweep rate. Here I p is peak current in amperes, n number of electrons involved in reduction or oxidation, a area of the electrode which is exposed to the solution in centimeter square, d diffusion coefficient in centimeter square per second, and c concentration in mole per liter, and finally v scan rate in volts per second. This curve we have seen earlier also. This is a typical linear sweep voltammogram which is giving you a peak. In linear sweep voltammetry, as from Randall-Sevcik equation, the peak current is directly proportional to the concentration, and therefore, if we plot peak current for different concentration of the solution, we get a linear curve which is known as calibration plot, and this is the basis for qualitative and quantitative determination of molecules by using voltammetry. In cyclic voltammetry, it consists of cycling the potential of an electrode which is immersed in an unstirred solution of the electroactive species and then measuring the resulting current. In short, we write cyclic voltammetry as CV. It is an extension of LSV, that is linear sweep voltammetry, in that the direction of the potential scan is reversed at the end of first scan, and the potential range is scanned again in the reverse direction. The species formed by oxidation in the forward scan can be reduced on the reverse scan. Similarly, species formed by reduction in the forward scan can be oxidized in the reverse scan. Here you can see we are beginning our cycle, we are seeing a reduction peak, and then when the direction is changed and when we move towards the initial potential, we see an oxidation peak. Here we are probing the fate of the product formed in the reduction, and we can see here that the product is oxidizing, and therefore, we determine the peak potential for cathodic peak and peak potential for anodic peak, and similarly we can calculate the anodic current and cathodic current for the cycle. The potential difference between the reduction and oxidation peaks is theoretically 59 millivolt for a reversible reaction. Delta E p is equal to peak potential of anodic peak minus peak potential of cathodic peak. The number of electrons transferred in the electrode reaction, that is small n, for a reversible couple can be determined from the separation between the peak potentials. Here, this value of delta EP is equal to 0.059 divided by n volts or 59 millivolt divided by n. The larger differences or non-symmetric reduction and oxidation peaks are an indication of a non-reversible reaction. From Rendell-Sevcik equation, IP is directly proportional to concentration, which is the basis of quantitative determination by using this technique. Thus, if all other parameters are constant, the plot of peak current versus concentration will be a straight line, and thus concentration of a species can be determined by using voltammetric analysis. Let us consider few applications. CV is widely used for the study of redox processes. CV determines the rate of electron transfer between the electrode and analyte, stability of the analyte in the electrolyzed oxidation states. It provides information about the number of redox states and the stability of these states. Fast and simple method for the characterization and mechanistic studies of a redox active system. Let us now come to pulse techniques. The primary advantage of the pulse voltammetric techniques such as normal pulse or differential pulse voltammetry is their ability to discriminate against charging current or capacitance current. These measurements can be made to study the redox properties of extremely small amount of chemicals because of following two features. First, the effect of charging current can be minimized and therefore sensitivity is enhanced. Faraday current is extracted or electrode reactions can be analyzed more precisely by these techniques. The two most important pulse techniques we know are differential pulse voltammetry, square wave voltammetry. Let us now come to differential pulse voltammetry. It can be considered as a derivative of linear sweep voltammetry or staircase voltammetry with a series of regular voltage pulses superimposed on the potential linear sweep or stair steps. The current is measured immediately before each potential change and the current difference is plotted as a function of potential. By sampling the current just before the potential is changed, the effect of the charging current can be decreased. The detection limit in this case is about 10 raised to the power minus 8 molar. Here you can see this is a linear ramp and we are superimposing with pulse at different times. The result is when we plot the difference of currents before the application of the pulse and after the application of the pulse, and second before the application of the pulse and after the application of the pulse, then we get a peak like shown here. This is the advantage of differential pulse voltammetry. In stripping voltammetry, it is a two-step technique in which the first step is pre-concentration, which consists of the electrolytic deposition of a chemical species onto an inert electrode surface at a constant potential. This pre-concentration step can involve either an anodic or cathodic process. The second step consists of the application of a voltage scan to the electrode that causes an electrolytic dissolution or stripping of the various species on the surface into solution at characteristic potentials. Usually, Mercury electrode are used for stripping voltammetry. Three types of stripping techniques are available. First, ASV, that is anodic stripping voltammetry. Second, CSV, which is cathodic stripping voltammetry. Third, adsorption stripping voltammetry. The waveform is plot of potential applied to the working electrode versus time and consists of several discrete steps. The deposition potential is applied to the working electrode to deposit the material onto the surface of the working electrode. The selection of the deposition potential depends upon the material. For example, if we are taking various metals, we must know at what potential these different metals undergo reduction, and therefore, we have to select a potential at which all these metal lines should reduce. Here, in the beginning, the metal is deposited at the surface of mercury, and then when we strip, then the potential decreases. So, in the beginning, the potential is constant, where our metal ion M2 plus is taking 2 electron to give metal, which is forming amalgam with mercury, and then this amalgam, when we strip, gives desired metal ion at a particular potential. Here you can see when we strip, the metal gives corresponding reduction peak. Say for example, we have two metals in the solution, we are reducing them at fixed potential. Now, when we strip from -1 towards 0, the first metal gives Cd2 plus, that is cadmium is oxidized to give Cd2 plus 2 electron, and the second at the desired potential copper metal gives copper ions and 2 electrons, and therefore, we get two distinct peaks in the stripping process. Higher deposition time increases the degree of pre-concentration, making a greater amount of deposited analyte available at the electrode during the stripping step. That means, the deposition potential time should be sufficiently large, so that all the metal ions present in the solution undergoes reduction and they deposit at the surface of mercury. An excitation waveform is applied which strips the deposited material back into the solution. The current is measured versus the applied potential. The measured current at these potentials is proportional to the concentration of the analyte in the original sample. In the case of anodic stripping voltammetry, it is used to determine the concentration of trace metals. It consists of a deposition potential that is more negative than the half wave potential of the metals to be determined, and an anodic positive going scan to oxidize the reduced metal back into the solution. Anodic stripping voltammetry can only be used to determine those metals that exhibit appreciable solubility in mercury. Briefly, deposition, applied potential more negative than E half of the metal ion, say M plus is taking n electron to give amalgam MHG. Then the second step is stripping, scan in the positive direction, peak current is proportional to the concentration of M. MHG is giving you Mn plus n electron. In the cathodic stripping voltammetry, the mercury working electrode is not inert, but takes an active part in the formation of the deposit and results in the formation of an insoluble film on the surface of the mercury electrode. Deposition at a relatively positive potential where Hg plus ions can be produced. Hg is giving Hg plus electron. 2Hg plus reacts with 2x minus to give Hg2x2. An insoluble film is formed. Stripping in cathodic stripping voltammetry consists of a cathodic scan to reduce the deposited salt back into the solution. Then in stripping process, scan in the negative direction, peak current is proportional to the concentration of X. Hg2x2 plus 2 electron gives 2Hg plus 2x. Advantages of stripping voltammetry. The technique of stripping voltammetry has been used in trace analysis with relative ease and success in a variety of analytical applications. With minimal sample preparation, this technique is routinely capable of identifying and quantitating trace components from 10 raised to the power minus 5 to 10 raised to the power minus 9 molar with excellent sensitivity and selectivity. It can be used to make routine analytical determination at the sub ppm level. Stripping analysis has received an unusual degree of interest since it is the most sensitive electroanalytical technique currently available. In summary, today we learned about voltammetry, then linear sweep and cyclic sweep voltammetry. Then we learned polarography versus voltammetry, how it is different than polarography, the Randall-Shevchik equation, which is the basis for the current in linear sweep or cyclic sweep voltammetry, pulse techniques and stripping techniques, and finally, we learned applications. In the next lecture, we will talk about conductometry or conductometric titrations. We will see how these titrations are useful and they are based on ions, that is the number of ions, charge of ions present in the solution. Thank you.